Hi, we're gonna go over sections 10.1 and 10.3. This is for Chem 102. So we're in chapter 10 of our textbook. And this is just a slide showing you the different topics we're going to be covering in chapter 10 and the different sections. We're doing the first three sections today, 10.1 to 10.3. So first we're going to talk about energy. So a lot of this semester we're going to be talking about energy. Energy is, we think about energy changing between system and surrounding. So system is what we're interested in. Surrounding is literally everything else in the whole universe. We usually think about the surroundings only like right around the system, but technically it's everything. Thermochemistry is studying heat, and the heat is the transfer of thermal energy. So heat is actually a transfer of that thermal energy. Heat is absorbed or released during a process. We're going to use, think about thermal energy and heat, changes in thermal energy as heat, as the SI energy unit for joules. But often we use calories, right? So if you were thinking about, oh, I'm ingesting this food, it has this many calories in it, that's actually the amount of heat that food will give off when it breaks down in your body. So keep in mind, this is really important, the nutritional calorie is big C calorie, and a regular calorie is little c calorie. And a big C calorie is 4.184 joules, and a big C calorie is equal to 1,000 little baby calories. Calorie is similar to, is the amount that it would take to raise 1 gram of water by 1 degree C. So that's the amount of heat that we get a calorie from. So it comes from the specific heat of water, which we'll talk about a little later. When we lose heat from our system, we call that exothermic. So think about heat exiting the system. Heat exits the system. It goes to the surroundings. And so if you were to put your hand on something exothermic, like a test tube, it would feel hot to you because the heat would leave the system and go into you, so it'd feel hot. So combustion reactions, like this is showing here in this photo, would be an exothermic reaction. So we'd feel that heat to the surroundings, which we are a part of the surroundings if the chemical reaction is our system. Endothermic process is heat is transferred to the system, so it would feel cold. So if you touch something that feels cool, heat is being transferred from you to the system. And notice that we actually can think about energy being in our chemical reaction. So if the energy is a product, that's exothermic, meaning the energy is given off. If energy is a reactant, that's endothermic. Energy is like a reactant, it's going in, it's like an ingredient. All right, so thermodynamics is the study of all these changes. We have different systems in thermodynamics. We have an open system where we can exchange mass and energy. So it would be like an open flask where water vapor is going in and out, and also heat is going in and out. We have a closed system, which is something that you're going to do a lot in lab, which is where we have transfer of heat can go through the glass, but we're not really transferring matter anymore, transferring mass, because we've stoppered it up so the water vapor can't move in and out, or vapors of whatever you have in your flask cannot move in and out. And then ideally, if we're talking about, if you're talking about thermodynamics, usually we do want heat to be able to transfer. So we often are talking about closed systems, but sometimes we want to even put our closed system inside of something where heat is not going to be transferred, and that would be an isolated system. So like if we insulated our flask where no heat could be transferred in and out and no mass can be transferred in and out, that would be an isolated system. So these are just some terms that would be helpful for you to know. A state function, we'll talk a little bit more about in class if you have questions, but a state function basically is a property that doesn't matter how you get there, It just matters where you end up. So for example, if we live on the 4th floor, we can take the stairs or we can go up an elevator. It doesn't matter how we do that. We get to the 4th floor, for example. The magnitude of change only depends on the initial and final states of the system. So some of those states might be energy, pressure, volume, temperature. Like we're just looking for final minus initial, does not matter how we got to final. That's a state function. We're going to talk about the laws of thermodynamics in this chapter. The first law is that energy cannot be created or destroyed. So we transfer energy, we can change the forms of energy, we can't create or destroy energy. And so this delta U is the change in internal energy, and the change in the internal energy of the system versus the surroundings is actually the same but opposite, because we can't, if the energy is going to be coming out of the system, it has to be absorbed by the surroundings. So it's just the opposite of the surroundings. And then the change in the systems, this is the system's internal energy, is given by Q, which is heat, and W, which is work. Q is positive for an endothermic process. So if heat goes into the system, the Q would be positive. If the Q is negative, heat is released by the system, so it's given off, so Q would be negative. For W, for work, if the work is done on the system, the work is positive. If the work is done by the system, the work is negative. So if the system is doing something, it's a negative. The system is giving off the heat, the system is doing the work. If the surroundings are kind of doing the thing, maybe you can think about it like that, like the endothermic is the surroundings giving the energy flowing from the surroundings, or work is flowing from the surroundings, essentially, then it's positive. So here are some scenarios. So if heat is given off by the system, you have Q is negative. As work is being done by the system, work is negative. Heat is being put into the system, Q is positive. Work is being done on the system, work is positive. So like if this is a piston here, if the system pushes the piston up, the system did the work. If we push the piston down, we did the work. The surroundings did the work. So that's the difference there. Don't overthink this too much. There's a lot way more important concepts in this chapter than the heat and work stuff. So if you want to pause and try this worked example, up here, give you the answer. So show you just the top part here. So at the bottom of the screen, you have an example. If you want to pause here and see if you can calculate it, then here is the answer. And of course, you have lots of homework questions. So think about, all right, we're going to be using, they want the delta U, they give us the heat, which is Q, and they give us the work. Now we have to figure out if it's positive or negative, right? So absorbs heat would be positive, but if it does the work, that's going to be negative. So that's why they changed the 141 to the negative here. And then we're just adding those two numbers up. So in this example, we have a system where the pressure is changing because we have constant volume conditions. So if we have it in like a scenario where the volume cannot change, if we take the solid and we make some gas, the pressure is going to increase. So under constant pressure conditions, the volume would increase though. So if we have volume the same and we make some gas, like imagine we're forming gas instead of something that cannot expand, pressure is going to increase. If though we're forming gas and the container can't expand, the container will expand. And so here now we get this work, right? So work can be related to constant pressure and change in volume. That can help us figure out what the work is. So however much change in volume we have can be related to the amount of work that is done at that certain pressure. So we get this formula where work is related to the pressure that's constant and the change in volume. The pressure here is the external opposing pressure. So whatever the like atmospheric pressure is that's like pushing down on this, and the work is pushing against it. So that's why we're doing the negative here. And that change in volume is also usually pushing out. So work is related in this equation. So why don't you try this question down at the bottom, pause it. You can go back to this equation if you need to, and see if you can do these problems. So here are your answers. And if you have questions about any of this, now would be a great time to take a screenshot and text me. How did they get this? How did they get that? It's a great use of the text. Pay attention to your units. I think that's something that really is something that students don't like to do in Gen Chem 2 is units. So pay attention to how the units cancel, right? And that will really help you double check your work. And then here's the part C. And then the textbook also gives us these little think about it areas. So you're welcome to read through that. And if you have questions, let me know. So pressure volume work, this PV work, is done when there's a volume change under constant pressure, right? And we can actually take this W and substitute it in, so we can get the change in internal energy related to pressure and volume. Then if we have constant volume and no work is done because there's zero change here, so this term becomes zero, we can think about the Q at constant volume, that's what that V means, is equal to the change in thermal energy or internal energy. So Q at constant volume, the heat at constant volume, is equal to the change in internal energy. If we're at constant pressure, the volume is still changing, then we have to keep this term here because the volume is changing. If we just rearrange this, the Q at constant pressure would be the internal energy plus P delta V. So these are just different variations of these equations. And I think that it's important as you move forward in chemistry, think about how do equations change if you have different variables constant. So at constant pressure, we have to keep this here because the volume is changing. At constant volume, this term is going to go away because the volume is not changing. And so we have this function of a system called enthalpy. And enthalpy is the internal energy plus the pressure and the volume. The SI unit notes here are pascals are equal to a kilogram over meter over second squared. Volume is usually in a cubic meter for SI units. And so we have PV here, and this is giving us joules. So you can see that a joule is actually related to these things. So enthalpy is going to be in joules. These are all state functions, which means that when we have changes in them, they don't care about how we're getting there. So we're deriving this thing here, I think, but the main goal of this is at constant pressure, change in enthalpy is the same as heat. So if you are interested in the derivation, that's all here, but the main takeaway from this slide is change in pressure, or sorry, change in enthalpy is equal to heat. So I want you to think about enthalpy as like thermal energy. So that change in thermal energy is that heat at constant pressure. And we are mostly always working at a constant pressure situation in like lab and stuff because we're not changing the atmospheric pressure necessarily. But there are other ways to think about this if you do constant volume, but for our purposes, Q can be equal to, or heat can be equal to delta H. So change in enthalpy, which we can think about as the change in thermal energy, is equal to the heat, which is what we know the definition of heat to be. So the enthalpy of reaction is basically the enthalpy of the products, the thermal energy of the products minus the thermal energy of reactants. So change in anything is always final minus initial. So final minus initial, products minus reactants. Assume that everything is occurring in the lab at constant pressure. And again, because the Q and the enthalpy change are the same, so here this would be Q greater than 0. So Q of positive is endothermic, and Q of negative is exothermic. So the enthalpy positive, and change in enthalpy positive is endothermic. Change in enthalpy is negative is exothermic. You will see us just say enthalpy of reaction, but we mean change in enthalpy. So as you kind of go through, we are not always going to say change in enthalpy. We might say delta H. But if we're talking about enthalpy of reaction, it's the enthalpy change in the reaction. We're just not going to say the word change. So keep that in mind. Delta H is what we're talking about when we're talking about the enthalpy of the reaction. So for example, solid water turns into liquid water. This is melting, right? The enthalpy, the change of thermal energy is positive 6. This means the heat is positive 6.01 kilojoules per mole. What does this mean? This means that per 1 mole of water, we have to put in 6.01 kilojoules of thermal energy to get water to melt from solid to liquid. So you got to consider when you're going to use this, is it a constant pressure process? If it's not, we can't really use this, right? We're talking about this enthalpy related to the heat is constant pressure. What's the system? So the system is the water. What are the surroundings? Everywhere else. And so if it's endothermic, because it's positive, that means we have to put energy in. This should make sense to you. You have to put energy in to melt water from ice to liquid. Here's the opposite. Let's say we have this combustion reaction here. It gives off energy per mole. So the system is the chemical reaction. It's giving off that energy to the surroundings, and it's exothermic. So we would feel hot touching that test tube. Think about this when you feel cold when ice is in your hand and it's melting. Why does it feel cold? It's because the ice is taking the energy from your hand in order to melt. So that, where does that 6.01 kilojoules per mole come from? Your hand, if you're holding a piece of ice. We'll talk about the concepts a little more in class to try to help you with the endothermic, exothermic concept as well. So enthalpy is an extensive property. That means that it does matter how much you have. So usually we'll see enthalpy per mole. So if we double the amount of matter, we double the enthalpy, right? So if I have twice the amount of water I need to melt, the energy I have to put in is going to be twice that much. In this case, we're boiling, right? Liquid to gas or evaporating. If I have twice as much to evaporate, I'm going to have to put in twice as much energy. And then the units here refer to the mole of reaction as written. So if it's kilojoules per mole, we start with 2 moles, right? It actually, if we take this divided by 2, we're going to get the number. So it's per the way it's written in the reaction. And we'll talk about that in just a second and use it as a conversion factor. So thermochemical equations are normal equations, and then they're giving you the enthalpy change, the enthalpy information. But be careful, be aware of the states, because in some combustion reactions, gas is what's written for water, and some liquid is what's written, and they have different enthalpies because the enthalpy of this different state matters. There's a difference there. So just be careful of looking at the physical states. So we're talking about thermochemical equations, and we'll do more with this later. But if, let's say, we need for some reason to, we'll talk about the reasons why later, but multiply an equation by a factor, we have to multiply the enthalpy by that same factor. So if I multiply this equation by 2, I also multiply the change in enthalpy by 2. If for some reason we needed to reverse an equation and think about it in reverse, So if I had to reverse this, I'm going to change the sign. Because if moving forward is exothermic, moving in reverse would be endothermic, but it's the same number. We will do a lot more with this when we talk about what's called Hess's law. So I want you just to pause and see if you can think about what we talked about here. I'll give you a hint for this question at the bottom. This is representative of not 1 mole, but this number is representative of what is written here. And so we know number of moles of each of these in like a mole ratio, and we know this is the amount of energy for what's written here. So if we start with 75 grams of C6H12O6, how many kilojoules? Calculate the number of kilojoules that you need to do this reaction. See if you can do it first, try it, and then come back. Okay, so assuming that you've tried it, and even if you got it completely wrong, even if you were like totally stumped, that's fine. So first we changed our grams to moles, and then we can use our, let's see. Oh, wow. They're doing this very differently than how I would do it. Let me show you how I would do this because the textbook's doing it differently. So how I would do this is this number, 2803 kilojoules, is equal to 1 mole of this thing. The reason why I say 1 is because there's a 1 here, and it's a coefficient. Now, if I were talking about oxygen, it would be 6 mole. So I can use this as a conversion factor and make this a lot easier. So just start with your grams. And we can use our molar mass. And this should all be familiar. If you feel like, uh-oh, this is not familiar, then you can go back in your textbook and do a little bit of work there. Come into office hours, go to SI, get some refresher on stoichiometry. And then we know for every 1 C6H12, we have to put in 2803 kilojoules. Let's make this easy. I don't know why the textbook wants to make this more difficult. And then we can just do this all at once. Fairly easy. Don't let this be more difficult than it needs to be. Let's just treat it like dimensional analysis. Let's see, we want 3 significant figures, so 1170 kilojoules. Here. Maybe that's what you tried. Let's see, they did something strange where they multiplied the thermochemical equation by 0.416 by the number of moles. Okay, if this all makes sense to you, you're welcome to do it. I think it's just a lot easier to take what you're given, this number, and set it equal to whatever number of moles you have, like a mole ratio, and just use it as a conversion factor. But we'll do more practice in class. So hopefully this wasn't too bad. I will see you in class.